Welcome to the class 3 of Basic Electronics. Today we are going to discuss about what are the voltage sources and current sources. So here if we say it is the sources, we have two types. One is voltage sources and second one is current sources. The source which provide voltage to the circuit, the source which provide current to the circuits. Now here again the voltage sources are divided into two categories. One is ideal voltage source and second one is the practical voltage source. In the same way, the current sources are categorized as ideal current source and a practical current source. So what is the meaning of a voltage source? A voltage source is a two-terminal device whose voltage at any instant of time is constant and is independent of current drawn from it. Such a voltage source is called an ideal voltage source and have zero resistance, that is zero internal resistance. You have to remember one thing here is we can call the voltage source as an ideal when the voltage at any instant of time is constant and that source must have a zero internal resistance. Practically, an ideal voltage source cannot be obtained because all these sources have some amount of internal resistance. Always remember this, all the sources having some amount of internal resistances. So we can't call that voltage source as an ideal voltage source. But still we are using it in the practical or experiments. So due to this internal resistance, what is going to happen here is some voltage drop takes place and it causes the terminal voltage to reduce. The smaller is the internal resistance or a resistor of a voltage source, the more closer it is to an ideal source. So to make a practical voltage source as an ideal voltage source, here it is, we have to use the smaller internal resistance. That is, any device that produces voltage output continuously is known as the voltage source. It is a two-terminal device and it has a forcing function of EMF. So in this we have direct voltage source. It is the device which produces direct voltage output continuously. It maintains the same polarity of the output polarity, that is called voltage, that is positive or negative terminals remains the same. When load resistance, say RL, I am taking the load resistance as a R of L. When this load resistance R of L is connected across this source, current flows from positive terminal to negative terminal via the load. This is called the direct current because it has one direction. The opposition to the load current inside the DC source is known as internal resistance, say R of I. So R of I is the symbol which we are using to represent the internal resistance. The equivalent circuit of a DC source is the generated EMF, that is called the electromotive force, which is represented as EFG, in series with the internal resistance, say R of I, of the source as shown below. So this is the circuit which shows the direct voltage source. So here the generated EMF, which is nothing but E of G, is connected directly to the resistor as it is in the circuit. So here we can calculate the load current. I is nothing but E of G divided by R of L plus R of I. So R of I is nothing but the internal resistance of the source. R of L is called the load resistor or load resistance. So here we have to remember the Ohm's law, that is V equal to IR. So I is nothing but V by R. V equal to IR, that is nothing but I is equal to V by R. So here V, there is a voltage across the source. So that voltage here we are representing as a E of G. So I am taking this one as E of G. Then R, that is the internal, here R is the resistance. So here we have two resistances. One is called the internal resistance of a source, and second one is the load resistance, which we are representing as a R of L. So here I can calculate the terminal voltage V equal to E of G minus IRI, or I can call it as IRL. As V equal to IR, so V equal to IRL, because R here is nothing but our load resistance. So this can be calculated as E of G minus R I into I. So this is how the direct voltage source can be connected and calculated. Now go for alternating voltage source. A device which produces alternating voltage output continuously is known as alternating voltage sources. It periodically reverses the polarity of the output voltage when load impedance, say Z of L, is connected across the such sources. Current flows through the circuit that periodically reverse the direction. This is called the alternating current. So here you have to remember alternate current. That is nothing but it is periodically reverse the direction. So this can be represented as E of G. So the impedance is represented by Z of I and Z of L. So here we can calculate the load current, that is called IRMS, as E of G divided by Z of L plus Z of I, which is nothing but EG minus I of Zi, or you can call it as I into Z of L. Next, we have a constant voltage source. A voltage source which has very low internal impedance as compared with external load impedance is known as constant voltage source. In such a case, the output voltage nearly the same when load current changes. So usually in this type of a circuit, the internal resistance which is connected is nearly equal to 0.005 ohms. So this is the one of the internal resistance which is connected to make it nearly equal to the ideal voltage source. A voltage source is a two-terminal device whose voltage at any instant of time is a constant and is independent of current drawn from it. Such a voltage source is called ideal source and have a zero internal resistance. So zero internal resistance. So to make it nearly equal to zero internal resistance, one must connect the R of I with very low resistance. Practically, it is not possible to get an ideal voltage source, because even though it is a voltage source, we are connecting a very low internal resistance. So sources having some amount of internal resistances as practical voltage source. The voltage sources where we are using some internal resistances. So we are using that one for practical or experiment purpose. That is called practical voltage source. Due to this internal resistance, voltage drop takes place and it causes the terminal voltage to reduce. The smaller the internal resistance, we know that the voltage source, the more closer it is to the ideal source. So this is how the one of the output we are getting when you are connecting the ideal voltage source. Here you can see the output is constant for a very long time period. When you apply a voltage, so that source gives us a constant output for a very longer period. So this is one of the characteristics of an ideal source. So practical voltage source, what happens here is, as it consists of a small number of or a small amount of internal resistance. Here you can see a small change in the practical source. That is the output. There is a smaller variation compared to the ideal voltage source. That is because of the internal resistance, whatever the internal resistance we have connected to the source. In the same way, the current sources. An ideal current source is a two-terminal circuit element which supplies the same current to any load resistance connected across its terminal. So here a practical current source is represented as an ideal current source connected here with the resistance in parallel. So even though in this case you can see the output current is constant for a longer period. You can see here a load resistance is connected parallel to the circuit, and there is a small variation in the current source. That is because of the whatever the internal resistance we have connected across the load. Now let us go for Thevenin's theorem. What is Thevenin's theorem? Why we are using Thevenin's theorem? What are the uses of Thevenin's theorem? So here, any two-terminal network, you remember this? Any two-terminal network containing a number of EMF sources and resistances can be replaced by an equivalent series circuit having a voltage source, say E of naught, in series with a resistance R of naught. Any two-terminal network containing a number of EMF sources and resistances can be replaced by an equivalent series circuit having a voltage source E of naught in series with the resistance, say R naught, where E of naught is the open circuited voltage across the two terminals. You remember this? E of naught is nothing but open circuited voltage between the two terminals. R of naught is nothing but the resistance between the two terminals of the circuit obtaining by looking in it, that is the terminals with load removed and a voltage source replaced by their internal resistance if any, or any complicated network across its load resistance. Load terminals can be substituted by a voltage source with one resistance in series. So here this is one of the advantage of a Thevenin's theorem, that is any network where you are using a number of EMF sources, whether it's 2, 3, etc., and the resistances, a number of resistances, say 2, 3, 4, 5, etc., can be replaced by an equivalent series circuit having a voltage source. So here you have to remember, any source which consists of a number of sources can be converted into a single voltage source, and a number of resistances which are connected in that circuit, series circuit, which is replaced by a single resistance, that is single equivalent resistor in series with the resistance R naught. So this circuit helps us in study of variation of the branch is varied while the remaining network remains the same. Here it is, the current flowing through a resistor connected across any two terminals of a network by an equivalent circuit having a voltage source, say ETH, in series with a resistor, say RTH, where ETH is the open circuit voltage between the required two terminals called the Thevenin's voltage, and the RTH is the equivalent resistance of the network. We can see it from the two terminal with all other sources replaced by their internal resistances are called Thevenin's resistance. Here you can see suppose we have a source, say V of S, which is connected to the number of resistances in the circuit, which is connected to the load, say R of L, which can be replaced by an equivalent resistor or resistance of the circuit. That means you are converting the number of resistances to the equivalent resistance. Here it is. And we have to connect it to the load. So consider the two terminal circuit. The circuit, say here it is, the circuit enclosed by a dotted box can be replaced by one voltage, that is E0, in series with the resistance R0. The behavior at the terminals A, B, that is these two, A and B, that is output terminals A, B, and A dash, B dash is the same for the two circuits, and they are independent of the values of RL connected across the source or terminals. So here it is, the behavior at the terminals A and B and A dash, B dash is the same for the two circuits. What is the meaning of this is, as per the Thevenin's theorem, the number of internal resistances which are connected in the circuit can be replaced by a single resistor. Here we have the resistors, say R1, R2 and R3. After connecting R1, R2 and R3, if I measure the output at the terminals, say A and B, is equal to the equivalent circuit drawn. Here it is, that is A dash, B dash. When the internal resistances are converted into the single resistor, here both the output at the A and B and A dash and B dash are same. In order to find out the equivalent voltage source, R of L is removed first. First you have to remove the load resistor. Here it is, which is connected at the output, that is A and B. We have to remove the RL from the circuit. Now after removing the RL, it looks like this. So E, the source, R1, R2 and R3 are the output voltage. Here, the resistors which are connected here. Now the voltage drop across R2 is desired voltage, say E0. Here the current through R2 is E divided by R1 plus R2. So the voltage across R2 is nothing but E0 equal to E divided by R1 plus R2 into R2. So here we have to use the Ohm's law, that is V equal to IR. So the VTH, that is a Thevenin's voltage, is nothing but V of open circuit. That open circuit voltage is nothing but, that is the I into R2. That is nothing but E divided by R1 plus R2 into R2. So to find the internal resistance, now this is how we can calculate the equivalent voltage source. Now we have to calculate the internal resistance of the network, that is called the Thevenin's resistance or equivalent resistance. So the voltage source is removed. Here we have to remove, to find out the Thevenin's resistance or equivalent resistance, we have to remove the voltage source. Again we have to remove the voltage source, and we can say it is deactivated by the short circuit, as in the diagram you are saying. As the source does not have any internal resistance, if I consider it as ideal, and when the source does not have any internal resistance, then the R of TH, that is called the Thevenin's resistance, is nothing but parallel combination of R1 and R2, now which is connected in series with R3. So when we are saying parallel, that is when both the terminals of the resistor is connected to each other, we can call it as parallel. We can call it as parallel. Here you can see this terminal is connected to this, and the second terminal is connected to the second terminal. So this is how we can convert this one into the parallel circuit. So Thevenin's resistance is nothing but R of naught is nothing but parallel combination of R1 and R2 in series with R3. So we know that parallel combination is nothing but R1 into R2. Here you can see R1 into R2, that is R1 R2 divided by R1 plus R2 plus of R3, which is connected in series to this. Here you can see why we are calling this one as a series, because the second terminal is open here. So the output of this one, as there is no voltage source, we can directly calculate the internal resistance at A and B by using R1 R2 divided by R1 plus R2 plus of R3. Now once you calculate the equivalent voltage and equivalent RTH, which is known as the Thevenin's voltage or Thevenin's resistor, so this we have to connect like this. So this is the number of voltages in the circuit which are converted into the single source, which is nothing but Thevenin's voltage, and the number of resistances which are connected in the circuit when it is converted in terms of a single resistance with the same value, it is Thevenin's resistor. So now we have to connect the Thevenin's voltage to the Thevenin's resistor in series like this. Now it is connected, this part which is converted, that is this part you can see. Now R1, R2 and R3. Now these three resistances are now converted into a single resistor with a resistance of say Thevenin's resistance is now converted. Here you have converted the values of all these three into a single unit, and that unit you have to add to the circuit, and now this is connected across the load resistance. As per the Thevenin's statement, the load current is determined by the circuit shown above and the equivalent Thevenin circuit is obtained. So that is the load current I of L is nothing but our VTH. Now as per the Ohm's law, V equal to IR. So I is nothing but V by R. Now here that is a load current, the current across the load that is at this point is nothing but VTH divided by RTH plus of RL, where VTH is the Thevenin's equivalent voltage. It is an open circuit voltage across the terminal AB known as the load terminal. RTH, it is the equivalent resistance as seen from the where all the sources are replaced by their internal impedance RL is the load resistance. So steps to solve Thevenin's theorem. You have to remember the steps to solve the Thevenin's theorem. Step 1. Remove the load resistance, say R of L, of the given circuit. That is, if you have a circuit like this, during the first step, you have to remove this RL. Second one, replace all the sources by their internal resistance. Then, if the sources are ideal, then short circuit the voltage source and open circuit the current source. And next step, now find the equivalent resistance at the load resistance, that is called the terminals, known as Thevenin resistance RTH. Draw the Thevenin's equivalent resistance circuit by connecting load resistance, and after that determine the required response. It is applicable, the Thevenin's theorem is applicable where it is desired to determine the current through or voltage across any one element in a network.